Okay, are there any questions before we start? Okay, if not, let me continue with what we were talking about last time. And then we'll see how far we can go. So what we have learned for a long time is if we are dealing with small length sequences, then the time domain convolution is a good approach. But if I am interested in the same operation here, the polynomial multiplication, and think about n is 1024 or 16,000 something or 32,000 something, then obviously time domain solution will not be efficient. And the best way to solve a problem like this with long length polynomials is to solve that problem in the frequency domain. So in the case of traditional signal processing, we could do that by computing the convolution by the FFT. And so typically in a traditional way, if we are going to compute convolution of x and y, and these are say n point sequences, each is n point sequence, so then append, first of all, DFT of x times DFT of y, the inverse DFT of that is really not x convolution y, that's going to be the circular convolution of x and y, and that means that will be basically if this was, if you took this 2n point, 2n minus 1 point. So this is x convolved with y will be 2n minus 1 point. If each one of this is n point, then this is n plus n minus 1, 2n minus 1 point. And the circular convolution here, so if I call this linear convolution z, okay, so this circular convolution will be n points, so that first one will be z0 plus zn, next one will be z1 plus zn plus 1, and the last one here will be n minus 1, but the one before that will be zn minus 2 plus add n to that, so 2n minus 2. Okay, so that's going to be the circular convolution, and that's called it's also called earliest sum. Okay, so you probably remember a little, and one way to avoid the one way to make sure that the linear convolution and circular convolution are same results, then we can append. So if we append n minus 1 zeros or n zeros to both x and y, and then compute 2n point DFT and DFT inverse, all 2n point, then the linear convolution will be same as circular convolution. Okay, and we have seen some of that is equal to circular convolution. Okay, so that's kind of a little background of what we know from our class on DSP. So what we are interested in talking about today is how does that kind of concept apply to computing the product of polynomials in the ring, and in particular we want to compute that modulo x to the power n plus 1, and we also want to make sure that all these coefficients are in the range 0 to q minus 1, where q would be the value, just like the value, maximum value q minus 1 would be the maximum value of the coefficient. So in a little more formal way, we are interested in again I don't really need you to learn a lot about number theory in this class, but it's probably we will just talk a little about that, not too much. So if we consider the polynomial ring and the so-called R and Q, which is a ring of it, the coefficients are all integers, so that's ZQ of X, such that the polynomial will be evaluated always modulo x to the power n plus 1. All the numbers will be evaluated modulo Q. Okay, so how do we define? How do I define? I'm going to deviate from the notation that I used last time. So I used this cap A and cap B. I'm going to today use lowercase a and lowercase b, so that I can use cap A and cap B for the entity in the frequency domain. So slight change in the notation. Had I thought more, I would have used the notation last class as lowercase a. So AX and is equal to, so also let me just even use this as subscript, so A0 plus A1X. So AX is A0 plus A1X up to AN minus 1 xn minus x to the power n minus 1. Again, all these coefficients are less than Q, strictly less than Q. Bx is B0 plus B1x up to Bn minus 1 x to the power n minus 1. The problem that we are going to compute is still the same. So the same problem, we are interested in computing A times B modulo x to the power n plus 1. So that's what we want to compute. Ax times Bx mod x to the power n plus 1. Also mod Q, the coefficients have to be also modulo Q, but I'm not explicitly writing that down. As long as I say that we are working on that polynomial ring, it's well understood that all the polynomials will be modulo this, all the coefficients, all the J0, A1, etc. will be modulo Q. Okay, so let me define what we call the number theoretic transform, similar to FFT. So what are some of the fundamental differences? So I can define cap A of J, okay, let me use J. I could use K also, so okay, we could use K. So cap A of K, the entity of that sequence A0 through An minus 1, so this is entity of that polynomial A, and this is the kth coefficient. So I can write AK is summed over I equal to 0 to n minus 1, AI omega to the power I k. Okay, so and that index of k will be from 0 to n minus 1 as well. Okay, so what exactly is, so instead of dealing with the basis as the complex exponentials in the DFT computation, so omega is simply the nth root of unity. So that means omega to the power n mod q is equal to 1. And the formal way of writing that is omega to the power n mod q equal to 1, and that means omega to the power n is equal to 1, is equivalent to 1 mod q. Okay, so so that is that's the formal definition of entity, and similar to the IDFT, we can also define identity. So I can write identity A of I. So A of I. So I want to get back AI from AK, and that is going to be N inverse. N inverse, I mean, you can think of that as 1 by N, but such a thing doesn't exist. So think of that as N inverse. Okay, I don't want you to think of this as 1 by N. Think of that as N inverse. We'll see in a minute. Why? K equal to 0 to N minus 1 AK omega to the power minus IK. So everything is similar. So if you think about the DFT and IDFT equation, that 1 by N is here, and this is omega to the power IK, omega to the power minus IK. But omega itself is going to be the nth root of unity. So as one example, if I select this polynomial example here, and let's say that I select n is equal to 8 and q is equal to 17. So if I choose this n and q to be these numbers, so what would be omega? So omega, which would be the nth root of unity would be, so think about omega will be equal to 9 in this case. Okay, so by the way, all these are integers strictly less than q. Okay, so 9, think about omega to the power, what we want to satisfy is omega to the power n. So 9 to the power n, which is 8. Okay, 9 times 9, 80. Anybody has a calculator who can calculate what this is? Okay, sorry.
430.
Okay.
46721.
Okay, and can you take the remainder, divide by 17 and see the remainder? Okay, you can check that is equal to 1. So take the remainder with respect to q, which is 17. So all these are, nothing here is complex exponential, like the DFT complex exponential, which is a complex number. Everything here is a real number. All these omega, omega squared, omega cube, all these are real numbers. Not only, so for example, what would be omega squared in this ring? Omega squared would be 81. Omega squared 81 modulo 17. 17 times 5 is 85, so that would be 13. Right, so 17 times 4 is 68 plus 13 is 81. So everything will be an integer. So every operation here is going on. So there is no twiddle factor. Every twiddle factor is an integer. Integer strictly less than q. So with those simple definitions, let's try to see what would happen if I simply compute. So if we simply computed the entity of A and entity of B and take the product and compute the entity inverse, we will get the what is the earliest sum. I mean that is what we would expect to get. So if I compute AK, so if I compute AK times BK, AK is equal to summed over I equal to 0 to n minus 1, AI W to power IK, BK is summed over I equal to 0 to, if I'm going to take the product, I might as well take another index, j to 0 to n minus 1, bj w to the power jk. Okay, so ak times bk is going to be the double sum over I and j, ai bj omega to the power I plus j times k. Okay, so and then if we are going to compute the product, so let's say that the product px, so the product px, which is ax bx, that's what we want to compute. So what I am going to compute now would be the earliest sum. So let's say that entity inverse of akbk, so if I just take the inverse entity of that, and that is going to be, so apply the inverse entity, so that's going to be n inverse. By the way, in this particular example, n inverse, if n is 8, n inverse is going to be 15. So you can see that n multiplied by n inverse modulo q should be 1. So 8 times 15, 120 divided by 17, 17 times 7, 119, remainder 1. So that's n times n inverse is 1 modulo q. Okay, so that kind of, so that's how everything is real number. Okay, so n inverse, which don't think about n inverse as, so that's why I don't want you to think at this as 1 by 8, because that's not the case. So that's n inverse. N inverse is an integer strictly less than q. So n inverse of akbk, so n inverse, so I can't use this index k. Let's see here. I could use, okay, so we have, yeah, I could use index k, that's fine. Entity inverse is going to be something that's not k, because we are summing over k. So yeah, so k equal to 0 to n minus 1, and then akbk, which is this double sum. So that's summed over I, summed over j, ai bj, omega to the power I plus j times k. Okay, and then this omega to the power, so instead of computing ai, let's compute al, because I don't want to use that notation I, because we are using that as a summing index. But let's correct that right here. So al and minus lk. Okay, so that way we don't get confused. Okay, so that omega minus lk. Okay, so this is going to be the Lth coefficient. Yeah, so I guess I could really call this ZL. Okay, so Z lowercase l. Okay, so let's call this one as ZK. Okay. All right, so then if I go through the summing index, k goes inside, I and j double sum comes outside, so summed over I, summed over j, ai, bj, and then summed over k equal to 0 to n minus 1, omega to the power I plus j minus l times k. And like the complex exponential, this sum will be 0 unless, so this is going to be 1 added n times, if you remember from adding complex exponentials, which can be thought of as Well, in the complex exponential case, you can think of them as adding n phasors or n vectors. So in this case, if you add these, this will be equal to n if I plus j minus L is either 0 or n. Then that n and n inverse modulo by the way, I am not saying anything, everything here is modulo q. So everything that we are describing is mod q, and I'm not writing those down, but you have to keep that in mind. And is 0 otherwise. So that means that this whole sum will have a value when I plus j minus L will be either 0 or n. So we can forget about all the 0 terms, and what remains then is when this is n times n inverse became identity or 1 mod q, and then I can write this as a so what does that mean? So that means j, so if I want to write this as I equal to 0 to, okay, let's just write down as 0 to n minus 1, and you will see in a minute, and then ai substitute j, so what is j? J equal to L minus I. This is I. So j is equal to L minus I. So again, the double sum reduces to a single sum. Okay, so the whole thing here limits us to that condition, and you can quickly recognize that's just becoming the convolution. But you will see that for a given L, let's say that n was 20, let's say n was 20. And for a given L, let's say L is 8. If I'm computing 8th coefficient, okay, so if L is 8, then this is 8 minus I. 8 minus I will become negative if I is greater than 8, right? So if I is greater than 8, so if this was L was 8 minus I, and if I is 9, that B has index has to be minus 1, which doesn't make sense. So the one way to think about that is this, to write that as two sums, L equal to 0 to L minus 1. So if I is 0, then this is AI, BL, which would be B8 in this case. If I is equal to L, then that would be A8, B0 in our example of L equal to 8. Plus, for I equal to L plus 1 to n minus 1, now take the condition that I plus j minus L is equal to n. So this will become then AI, BL minus I plus n. Okay, so then in fact you will see that if I is L plus 1, then this whole thing will be n minus 1. So that's how we can make sure that the index of A and B, in particular B, will be non-negative. And that is precisely what I just described in the context of traditional computation, where the part that was so what you are seeing here is really the earliest sum that I was describing, right? So that's exactly what is earliest. So it is not really surprising that just taking the endpoint entity, taking the product and multiplying them and taking the I entity simply gives us the earliest sum, and so that's not what we want. So that's not what we want. So how then do we solve that problem? Well, we can just do exactly what we do in case of DFT. So we can definitely append zeros and compute two endpoint entity. Okay, so so this is a lowercase n, okay, 2n point entity I entity, and let's just try to see if that is indeed computing the correct thing or not. And so to look at how we can compute, okay, so maybe let me not worry about that. So that method will be okay. So we can work on that, and so just like the convolution problems that we work on, once we compute the 2n point, then we have to manually do the modulo and then add back those terms after n minus 1 so that they circle back. So this will work. So what we really want is something where we can use only n point. So how do we use only n point entity? So if you think about this method of computing an Elias sum as something called a positive wrapped convolution. So what we have computed here is called positive wrapped convolution, which is what we don't want. And to negate that effect, to negate the effect of this wrapping, we can use a negative wrapped convolution. And here we do not compute, no need to compute 2n point anymore, because we will only compute n point, entity and identity. So that's what is called a negative wrapped convolution. But it requires some pre-processing and post-processing. So in order to only compute n point entity and n point identity, it requires some pre-processing and post-processing in combination with the n point entity and n point identity. So what is the pre-processing that we are interested in? So the way that the so-called negative wrapped convolution works is so instead of starting with AI to compute AK, we do some pre-processing to get AI tilde. So think about the polynomial. So think about this polynomial AX. Instead of dealing with the polynomial A of X, let me think about some pre-processing where the coefficients are changed in a way. So think about a polynomial A tilde of X, which is A0 plus A1 psi x plus A2 psi x, psi squared x squared, up to A to the A n minus 1 psi to the power n minus 1 x to the power n minus 1. So what did we do? So we take the coefficient AI and change that to AI psi to the power I. That's the pre-processing step. So every coefficient in the original polynomial is now multiplied by the psi to the power I. Okay, and what is psi here? Psi is now the 2nth root of unity. So that means psi to the power 2n will be mod q will be 1. Okay, so that is the difference. Remember that omega was nth root of 1, so omega was nth root of 1, and psi is 2nth root of 1, 2nth root of 1. So that means omega is equal to psi squared. Okay, that's one way to think about it. So in this particular example, if I want to think about Okay, so okay, so let me, so in this example, we already knew omega is 9, so psi will be 3. Psi will be 3. So omega is the square of psi. Okay, so so that's kind of that's the pre-processing step. So A is, instead of taking the entity, so of A we will take entity of polynomial coefficients A tilde. So think of A tilde I is equal to AI times psi to the power I. Okay, so that's, and then B tilde I will be same B I psi to the power I, and I'm not writing this down, but so B tilde X is written exactly the same way. B tilde X is going to be B0 plus B1 psi X plus B2 psi squared X squared, exactly the same way, and then B I tilde is Bi psi to the power I. That's our pre-processing step. So if I pre-process the coefficients of Ai and Bi by multiplying them by psi to the power I, then I get a new polynomial Ai tilde and a polynomial Bi tilde. And then if I now take the entity of, so I can say that, let's say, so we compute the entity, so let's say that the entity of so-called Ai tilde is now Ak tilde, entity of Bj tilde is now Bk tilde. So we will take the entity of the coefficients so Ak tilde, so I'm just going to write down from here, Ak tilde is equal to summed over all I, Ai psi to the power I, that's our coefficient, multiplied by omega to the power Ik. Okay, so that's Ak tilde. Bk tilde is same way, and I'm going to again use that notation, summing index j, bj psi to the power j, omega to the power jk. Okay, so then I take the product Ak tilde times Bk tilde, and that product, so I can say that product, so let's now call that product Pk tilde, because what I want to denote that result finally as P of x, the product of, I think that's what I used last time. So the product of Ax times Bx mod x to the power n plus 1 is Px. So we are going to compute P tilde x. Okay, so P tilde x, so let's just say P tilde x will be let's say the coefficients of P tilde x will be equal to the point-wise product Ak tilde Bk tilde, and k ranging from 0 to n minus 1. So the whole polynomial P of x will be A0 tilde B0 tilde plus A1 tilde B1 tilde x plus A2 tilde B2 tilde x squared, and so on. That's a polynomial. Okay, so let's keep these coefficients, and let's call this Pk tilde. So this is Pk tilde. Okay, instead of calling Zk, Pk tilde. And then what I want to then compute is what I want to show really is the entity inverse of that is indeed Pk, exactly what we wanted. So that's what we saw last time, P of x. And in this example, we computed all those coefficients P0, P1, P2, P3. And so what I want to at least be able to prove that through this negative wrapped convolution process, we should be able to get back after a little post-processing pk. So how do we get to that point? Okay, so inverse entity of pk tilde is equal to n inverse, let's just use the same summing indices so that we don't make more than necessary mistakes. 15.4, well, okay, let's n inverse times summed over L, so I can call this as PL, so this is lowercase, this is uppercase, PL, so in the time domain, PL tilde. Okay, so this is n inverse K equal to 0 to n minus 1, then I, J, AI, Bj, psi to the power I plus j, omega to the power I plus j times k times omega to the power minus L k. Okay, so the time domain coefficient is L, that's why this is L, this is k, and that's why this is k, and that sum is k. So if we then take this to the outside exactly in the same way that I was working out in the beginning and see where that goes, 15.2 and 3, okay. Okay, so let's take a look here. So yeah, so we do everything same like that. So n inverse summed over I, summed over j, a, I, b, j, psi to the power I plus j, omega to the power I plus j minus L. By the way, times k, summed over all k, and that quantity is equal to n if I plus j minus L is equal to 0 or n. Okay, so so then we can say so this is equal to, so that n and n inverse will cancel out, mod q will become 1. So if I write this down as again as two terms, so what will happen here, okay, so I plus j is either going to be L or L plus n. Okay, why am I talking about that? This power I plus j will be either L or L plus n. So I can write this as again the same way as two different sums, but now this will be I equal to 0 to L, AI, and j is going to be L minus I. Okay, times psi to the power I plus j is L. For the next term, I equal to L plus 1 to n minus 1, AI. Now I have to use I plus j minus L is equal to n, and j is going to be L minus I plus n, and that psi to the power I plus j, and I have to use that I plus j as L plus N. Okay, so that's how that's two sums become slightly different with this pre-processing of these psi terms. Okay, so now I can recall that psi to the power n is minus 1. Remember, psi to the power 2n is 1. And that means psi to the power n will be, minus 1 mod q, still minus 1. Okay. And then that psi to the power l here is minus 1, so that plus becomes minus. Okay, psi to the power n will become, and then psi to the power l in both places will come outside a bracket. So then I can write this as psi to the power l outside the bracket summed over I equal to 0 to L A I B L minus I minus, why minus sign? Because psi to the power n is minus 1. Okay, minus A I B L minus I plus n, and that is PL tilde. So what I really want is this quantity, so PL. So ultimately to compute PL, we need to multiply PL tilde by, so PL is going to be psi to the power minus L times PL tilde, and that is the post-processing step. Okay, so if you will see what we were able to accomplish with that minus sign is exactly what we were manually observing last time. So with that, whenever the indices became more than, degree became more than n minus 1, so that's what is happening here, this minus sign. So minus of this whole thing, x to the power 5 became minus x, minus of that whole thing, x to the power 6 became minus x squared, minus of that whole thing, and that's really this minus of this whole thing. And that is why the so-called negative wrapped convolution is, we have now shown that it indeed is computing what we want to compute. So the steps basically are, so you start with AI, multiply by psi to the power I, take b to power bi, the coefficients, psi to power I, and then take the entity, and then take the product, and then take the I entity or inverse entity, either way, and then multiply by psi to the power minus, I can say minus I, it doesn't really matter, minus L, or, and that will be what we want Pi. So that is called negative wrapped convolution. Okay, so any questions so far? Obviously, I think it is normal to assume that you won't understand this very quickly. I mean, that is perfectly reasonable, and of course some of you will understand very quickly here. So I have posted the couple of examples from this, so some examples in the handout, so look under that handout. So here are some examples. If we start with, so these are in your handout, so you don't have to worry about this. Your homework will ask you to do something like this, but with a different polynomial as opposed to the polynomial that I've started with. So I've started here AX is same as BX, which is 1 plus A0 is 1, A1 is 2x plus 3x squared plus 4x cubed. That's kind of what I started with, and what we are then computing is 1 plus 2x plus 3x squared plus 4x cubed. A times B becomes whole squared mod x to the power 4 plus 1, and that's what we are computing. And if you look at, it looks like here the final results would be 10 plus 11x plus 14x squared plus, no, this is A1, 10, so that result should be 10 plus 14x plus A0, A1, A2. This should be a 3. Should be a 3, not a 4. 10 plus 14x plus 11x squared plus 3x cubed. Okay. So that's what it should be. And if you take this process here, so what you see here is the 4-point sequence 1, 2, 3, 4 is appended with 4 zeros. So the A and B both are same. These are appended with 4 zeros, and then we go through the entity, which is exactly same as the butterfly that you have already seen. And in this case, this is decimation in frequency. The time domain samples are in place. And so try to understand how these things are always computed modulo. Let me take one example here. Psi 8 to the power 4. Okay, so psi is 3. 3 to the power 4 is 81. 81 mod 17. I think we calculated that as 13. Okay, then 3 times 13 is 39. 39 mod 17. 17 times 2, 34. Remainder 5. All these things, that's how you have to trace these things. So trace all this, do it at home, and you will do it as part of your homework. And then we get these A's and same as B's. And then we take the product, A times B. 10 times 10 is 100. 100 mod 17. 17 times 5, 85, remainder 15. So that product 10 times 10 is equal to 15 mod 17. 15 times 15, 225. 17 times 1, 17, remainder 5, 55. 17 times 3, 51, remainder 4. So 15 times 15, mod 17 will be 4. And you check all these things. And then take these coefficients and place them for I entity, and finally to the n inverse. By the way, n inverse is 15. 8 times 15, 120. 17 times 7, 119, remainder 1. So these are the n inverse multiplied here, and you finally get back the final result. So that's what we are getting here. So think about how to compute those, and then manually you have to manually compute these things, right? So A0. Let's see what we have here. A0, where is A4? Something doesn't seem right, so I guess, yeah, so I think I didn't write that correctly. I'm not sure what is here. A0 plus A4 is, what did you write here?
It should be minus A0 minus A4.
A0 minus A4, okay. Yes, A0 minus. So 0 minus 1 minus 8. Minus 7 mod 17. Right, okay. Minus 7. 1 minus 8 mod 17 is 10. Okay, so check all these things. So you check all these things. Okay, so now, so that's by appending zeros. And how do I use the negative wrapped convolution? So the negative wrapped convolution says, take these AI multiply by psi to the power, by the way, this psi 8 means 8th root of unity. N is 4, so this is the 2nth root, so n is 4, psi 8, and multiply them by psi 8 to the power 1, psi 8 squared, psi 8 cubed. So again, check what these things are. You will do that in your homework. But this is kind of given you as an example, so you at least verify that you are learning how to compute these things. And then as another example, let's say how do you do the modular add. So 12 plus doesn't seem right. 12 plus 1. So what did you do?
1 minus 12.
1 minus, so this is the minus, yeah, 1 minus 12. So 1 plus 12, so in this butterfly, 1 minus 12, thank you, 1 minus 12 is minus 11 mod 17, so add 17 to that, you get 6. Okay, so then the entity continues, the post, multiply all these, you get the modulo with 17, and I entity, everything is fine here. All is an I entity, just as you have seen IFFT, similar to that. Finally, we multiply by n inverse. N inverse is 13 in this example, n is 4, 4 times 13, 52, divide by 17, 17 times 3, 51, remainder 1. So n times n inverse is 1 modulo 17, so multiply by n inverse, so these are multiplying by 13, and then the final post-processing step, multiply by psi to the power minus L. Okay, so that's psi to power 0, psi to power minus 1, psi to power minus 2, psi to power minus 3. That's called the post-processing. And that's the final result, which 10, 11, 14, 3, 10, 10, 14, 10, P1 is 14, 10, 14, 11, 3, and that's the same result. So we are able to get the same result now with a little pre-processing and a little post-processing, but only computing n-point entity and n-point I entity by the so-called negative wrapped convolution. Okay, so any questions so far? Have I confused somebody? Well, it is good to be confused. It's good to be confused, then you think through it, and then you do your homework, and then it becomes clearer. Okay, I've given you this chart as an example for you to learn first and then do the homework. By the way, I'm a little late in posting the homework, but I should be able to post them, if not by tonight, by tomorrow for sure. Okay, so you can check tomorrow morning or late tomorrow afternoon sometime. So then the next question arises, is it possible to compute n-point entity and n-point I entity without going through these pre-processing and post-processing steps? So that's kind of the next question. So is it possible? So this so-called, what is written here as low complexity entity and low complexity I entity, is really trying to optimize this process here and trying to eliminate these pre-processing multiplications and these post-processing multiplications. Okay, so that's the last piece of the puzzle. So we started with straightforward approach, append zeros, and then we went through the negative wrapped convolution, and then how do we reduce the complexity of the negative wrapped convolution by eliminating these multiplications. So that is our last piece of the puzzle, and how can we achieve that? Okay, so that is, by the way, the handout, in the handout section you will see the preprint paper, not published, preprint paper under archive, and I don't want you to read that whole paper, that's not necessary, only read just one section, 3.a, and that's what I mentioned to you to read. Okay, so okay, so now to further optimize, so we can compute So if I start with, so the whole idea here, the main idea here is to somehow, so think about what we are trying to accomplish. What we are trying to accomplish is, in some sense, modifying the entity so that the twiddles are slightly different and these coefficients can be observed into the twiddles. That's really what our goal is. So that's kind of where the optimization comes from. So if I start with that equation AK tilde, which is given by this quantity, so if I write that down as sum of even and odd, okay, so so the even terms, collect these even terms, so I can write that as summed over sum L equal to 0 to n by 2 minus 1, a 2L, and these are the even coefficients, psi to the power I. Okay, so I is now replaced by 2L times W or omega to the power I k is 2LK, plus if I take the odd terms, L equal to 0 to n by 2 minus 1, a 2L plus 1, replace I by 2L plus 1, psi to the power 2L plus 1, omega to the power 2L plus 1 times K. Okay, so now is a good time to think about how to optimize this here. Okay, so so the second sum, so this is side. First of all, think about how many. So think about what is this quantity representing. So if you go back and think about what we were trying to do, and in a way, you know, so this is an n by 2 point sequence, n by 2 point sequence. So that means I can think of this as an n, computing an n by 2 point entity, n by 2 points. So that means, so remember in previous DFT problems, we were bringing that 2 to the denominator, and so in a way, if I put back here psi to n, because that was the 2nth root of unity, okay, so psi and put back omega is the nth root of unity, so psi 2n to the power 2l will be psi n to the power l. Okay, so so that's really, well, by the way, the psi n now will be same as omega n, because that's the 10th root of unity. And then omega n to the power 2lk is same as omega n by 2 to the power lk. Okay, so you already remember some of those kinds of things. And what about here? I have to take this outside. Psi to the power 1 does not depend on summing index L. This plus 1 times K. So I can throw this out and place them here. Psi and omega to the power K. That to the power K came outside the sum. Psi came outside the sum. Okay, so now what I have is something that looks like, okay, this is something that looks like some kind of an n by 2 point entity of the even, some kind of n by 2 point entity of the odd, and then if I want to compute a k plus n by 2 tilde, what will happen here is, so this first sum is going to be there, okay. The next sum is going to be psi times omega to the power k plus n, okay, times something else, okay, and that omega to the power k was here, and that omega to the power n, something doesn't seem right. Did I make some mistakes? Omega to the power k. I should be getting a negative sign. So omega to the power n is plus 1, which is what I don't want. So there is something. Do you see, Shinwei, where I made a mistake? Okay, so I can update my note and try to show you why that should be minus. And you will see that exactly those are exactly the equations that we have seen in merging equations in the DFT. So what finally have we accomplished? If you look through these things, the new so-called new twiddle factors. So the new twiddle factors, okay, let's take a look at the new twiddle. So instead of having omega to the power lk, so let's write this equation down and see if I can rewrite the new twiddle factors. So now the new twiddle factors, summed over L equal to 0 to n by 2 minus 1, a to L, okay. So omega is psi squared, okay, so I can write this as psi to the power 2L, psi to the power 4LK. So we are substituting omega is equal to psi squared, and that becomes L equal to 0 to n by 2 minus 1, a to L, psi to the power 2 taken outside a bracket, 2 taken outside a bracket, 2L plus 1 times KL. And so I can cancel that. So if I add psi to n here, I can cancel that 2 by making it psi n. Okay, so that's final. That's really what the new twiddle is. So if you think about what these twiddles are, and it doesn't matter if it is expressed as omega or psi, it doesn't matter, and that's this. Instead of just having, no, there should be no more. 2, so let's see, 2L, so 2L taken outside a bracket times 2K times 2K. Okay, so that is that's the twiddle. That's the twiddle. And so instead of having omega to the power KL, that new twiddle is going to be 2K plus 1 times L. And so if you look at the, so these 2K plus 1 will be odd numbers. And that's why if you look at these twiddles here, these are to the power 1, to the power 3, these are odd numbers. I realize I've gone over this without a lot of detail, but I think maybe For a simple example like n equal to 4, by tracing this, you should be able to get the right answers. That is the low complexity entity. So the final question then is what happens to the I entity? So how do we finally reduce the complexity of I entity? Okay, so for this case, we want to compute pk tilde is equal to n inverse summed over I equal to 0 to n minus 1 maybe I shouldn't be using k, I should be using L here. Yeah, I should be using L here and should be using k here. Okay, so PL tilde is equal to summed over all k, pk tilde omega to the power minus kl. Okay, that is the equation for the p tilde. And if you recall what we were trying to compute, so we are interested in computing PL, that's what we really want to compute. And we had seen that PL was psi to the power minus L times this tilde. So, okay, psi to the power minus L times this whole thing, so that's N inverse k equal to 0 to n minus 1 pk tilde omega to the power minus kl. Okay, and then I can write this as two terms. So take the first half Okay, so we have written that as sum of two terms, and then if we take k minus n by 2 is equal to some k prime, and finally put back that k prime as back as k, so this will be k prime will be 0. So okay, so k prime equal to 0 to n by 2 minus 1 k is going to be k prime plus n by 2, and that k is going to be k prime plus n by 2, and then get rid of the dummy index prime, so this prime doesn't matter anymore, that's just a dummy index. So then what do you see between these two terms? If I take this omega to the power n by 2, what is omega to the power n by 2? Omega to the power n is plus 1 mod q. So this will be square root of 1 minus 1 mod q. And then if we take this quantity outside here, okay, so So then there will be a negative sign, then I can take these two together. So then we will get, so let's see what we will get. So n inverse psi to the power minus L summed over k equal to 0 to n by 2 minus 1 pk tilde Okay, so I think so what you see here, that minus 1 to the power L has to be, okay, let's put this here, minus 1 to the power L, whole thing in a bracket, times omega to the power minus KL. Okay, so now we can evaluate separately P2L, and that minus 2 to the power 2L will be plus P2L plus 1, that's odd. So we can evaluate separately even and odd, and that will become negative. Okay, so those will be computing the even and odd, and there is a little more optimization to that. So I am going to skip that. I think you can see that from the final details. I may talk a little more next time, but the final details from the archive preprint, you can see that, and then you can check at home about this low complexity INTT. So there is a little more that I will talk about on Monday. I have skipped some last parts here, so I'll talk about that on Monday. But this is a good place to stop, and so we have definitely gone through how the long polynomial, because that's really what the level of security depends on, these long polynomial multiplications which are of length 16,000, 32,000, and these cannot be done in the time domain, so they have to be solved in the frequency domain, and using n-point entity and identity, we can compute them with n log n complexity as opposed to n squared complexity. So I'm going to complete the very last part a little bit here that's left next time, but yeah, so read. So next homework, I don't know what the homework will be. I'll try to complete it, but will be based on this class. Mostly the second exam is going to be on what we just completed right now. I mean, that's kind of what the second midterm exam is going to be about, and we'll move into new topics starting next class. And we will really move away from the whole class so far has been about fast structures, and with all these fast convolution, fast parallel filters, and fast polynomial multiplication, the goal has been to reduce number of multiplications. And so we will really jump into the next part of the class to high speed, and that's where we will begin talking about increasing sample speed of the systems by pipelining and parallel processing, but mostly when the computations are recursive. If you think about signal processing computations, whether it is an IIR digital filter or an adaptive filter or a decision feedback equalizer, when you think about a communication system, there are basically two things at the receiver. I mean, the transmitter is never the hard thing to implement. Transmitter is always a simple thing to implement. The receivers are always the hardest thing to implement. So there is a detector and a decoder, and both of those are feedback operations. And if we were going to implement them at high speed, and that's what we will be studying in the last part of the class. Okay, so I will stop here. No, this would be better. No, so okay, yeah, that's right. Yeah, so this is a separate sum. I equal to L plus 1.